Hello everyone. Today we are going to learn 5.3, the multiplication rule. So here is the learning objective. Okay, so let's take a look this example. You have online course. Question number 1, true or false. Number 2 is multiple choice. Okay, what is the probability that you get right answer, true, false, and multiple choice? Because you cannot see anything because your browser is not working. So what is the probability that you guess answer to both question correctly, right? Okay, so we had a tree diagram before. Let me just show you, right? So one is true and false. In the true, we can have A, B, C, D choices, and then in the false, we have A, B, C, D choices for multiple choice, right? Okay, here we go. Yeah, make sense? So this is a tree diagram. So we have a 1, 2, 3, 4, 5, 6, 7, 8 possible answers. Yeah. Okay. Then if uh this one is the correct answer, assume, yeah, this is the correct answer. Then what's the probability of we get the correct answer, right? So yeah, so in the case, the true false, correct, and the multiple choice is correct too, right? Okay, there will be number of, let me just make a detail over number of sample space, yeah? So we know how many sample spaces there? 8, right? How many true, false, correct, and multiple choice correct, right? So there is only one, right? So 1 over 8, which is 0.125, right? Okay, now, this is a lot of work, right? Tree diagram. How do we make a shorter process to get the answer quickly, right? Okay, so let us do this way. So we have a multiple choice, correct, and sorry, true, false, correct, and multiple choice, correct, right? Multiple choices, correct, right? Okay, then if we make a true, false, correct, and multiple choice is correct, right? Correct. Okay, so what's the number of true, false, correct over number of sample space, and then number of multiple choices correct divided by number of sample space. Yeah. Okay, so in that case, how many sample space there? True and false. Only 2, right? So only we have 2 sample space, true or false, right? And then how many correct? Only one correct from true, false, correct. True, false question, right? And then how many sample space in the multiple choices? We have 4 because A, B, C, D, right? A, B, C, D. And then how many correct? One correct, right? So if we multiply together, what do you get? So we have a 1 over 2 times 4, which is 8. Yeah, which is a 0.0125. So we get the same answer. Make sense? All right, then we have a formula, and then we have a terminology for this one. Okay, so we have two events, E and F, are independent if the occurrence of one does not affect the probability of the other. Okay, what this mean? I can give you the example. We have event E has, let me write down. Example, event E has rolling a die. And event F, flip the coin. Flip the coin, right? So the outcome of rolling a die does not affect the outcome of a flip a coin, right? Or vice versa, right? So we call event E and F are independent. Dependent. So don't get confused with this joint event. That's a totally different terminology. All right? Okay. Now, if we have independent event, then we have n. They give us n. Yeah? They ask us about what's the probability of event E and F. Then we just multiply of their probability. So we had earlier n part, right? What's the probability of event E and F? Then we just using overlapping part, right? That is just a regular in general, E and F. But then in here, in this section, two events are independent. If they ask us what is and, then we just multiply their probability. Make sense? Okay, so let us do this one. So we have, what is probability of rolling two six dice, two six-sided dice and getting double sixes, right? Okay, so what if we say that we had this one earlier, right? Okay, for this section, what if we say the event E, think, event E, rolling a die, and then event F, rolling another one, right? So basically two, right? Okay. Is this outcome affect to this outcome? Or this outcome affect to this outcome? No, because we have two different fair dice, right? So fair dice means the one side is more heavier, and then yeah. You know what I'm saying, right? Yeah. Okay. Say just okay. All right. So we understand, right? Yeah. So we're event ENF independent. All right. Then we can use the formula. We had the formula, probability of event E and F. Then probability event E times the probability of event F. Yeah. Okay, so in that case, we have what's the probability of getting 6? And 6. Okay, there will be what's the probability of getting 6 times probability of getting 6 again, right? All right, so there will be number of getting 6 divided by number of sample space and times number of getting 6 divided by number of sample space, yeah? So what's the number of sample space? So rolling a die, 6, right? Good, it's a 6. And getting 6, which is 1 out of 6, right? How about here? Same. So what do you get? 1 over 36, which is 0.0278. Which is we had earlier, right? So let me show you. Is it there? Yes. We have like we had earlier, right? The earlier section. So 1 out of 36. Yeah. To get also the probability. Remember? Yeah. Good. All right, so let us do this question. So we're flipping a coin 3 times. Also, this one we did that in the 5.1 section. So what is the probability of flipping a coin 3 times and getting heads all 3 times, right? So that means event E, flip the coin, event F, flip the coin. We have another event, E, F, G. Event G has flip the coin again, right? So 3 times. They are all independent event because their outcome doesn't affect the other outcome, vice versa, right? Okay, so independent flipping, flipping. This means independent event. Not this mean, this is, right? Okay, we want to answer all 3 times head and head and head. Yeah, so that is head times probability of head times probability of head. Yeah, that is what's the number of getting head out of sample space? Yeah, so what is the number of getting head out of a sample space? Yeah, what is the number of getting head out of a sample space? So there will be sample space, flip the coin 2, right? 2, head or tail, right? And then how many head? Only 1 head. So same thing, right? So 2 times 2 times 2, which is 8. So 1 over 8. Yeah. So that is 0.125, like earlier. Answer, right? Okay. Now let us do these questions. So find the probability of rolling 4 dice. So 6-sided. Yeah. Is there less than 6-sided or more than 6-sided? There's a special one, right? Yeah. Okay, never getting A6 on the face. So let us do that. So this is independent event, right? Yeah. Independent event. So we are using probability of not getting 6, not 6, and not 6. How many times? And not 6, and 4 times, right? Not 6. Okay, so what's the number of not 6 over number of sample space? And then how many times? 4 times. Yeah, I don't want to write. More easier way, right? So more easier. The mathematician always find the easier way in logical way, right? Yeah. Okay. Oh, what's going on? So 4 times. Okay, how many sample spaces there? 6. Yeah. One dice has 6 outcomes, possible outcome, right? Sample spaces there. And then how many not 6? 5 of them, right? 1 through 5. Yeah. Do you want me to write down? So sample space, we have 1, 2, 3, 4, 5, 6. And then not 6 means 0, not 0, 1, 2. We know 5, yeah? Okay, now can you please calculate that? 5 over 6. Oh, no. We have to do fourth power, right? Yeah. Fourth power. So using calculator, decimals, yeah? Power. So, or you might use head in your head, like in your calculator. Okay, so we have a 0.4823. Yeah, and then I never interpret, right? So we have a 48.23% of the time. You roll 4 dice, then you will get not 6s. Yeah. Are you guys okay? Very good. All right, so let us do this example. We have when driving to school, student must pass through 5 traffic lights that operate independently for each light. So all the lights is independent, right? There is a 40% chance that is green. Find the probability that all 5 traffic lights are green on a trip to school. So let us do this one. What's the probability of all 5, right? Greens. So independent, so we can use that. The first green and second on green. Okay, let me write down again. That means first green and second green and third green and fourth green and fifth green, right? All right. So that is first green times the second green and times the third green times the fourth green times the fifth green, right? Okay, so what is the probability of green? 40%, which is we are using 40%. There will be Beyonce method to the left twice without the percent notation, right? So pretend to point to there, decimal point to there, 1, 2. So that will be 0.40, yeah? Basically 0.01. All right, so we will get 0.40 times 0.40 times 0.40, tired, right? So until where? Fifth power, right? So 5 times. So what do you get? So we have a 0.0102. So there is about the 1% chance that all the traffic light will be green. Yeah, so 100%. That means to the right twice. So that will be 1.02%. So there will be about just 1% chance that all 5 traffic lights will be green. Yeah. Okay, so let's talk about the second part. Find the probability that none of the 5 traffic lights are green. Okay, so how do you do? None of green. Out of how many? 5, right? Okay, so that means the first one not green, right? And second one no green. And third one no green. And fourth one no green. And fifth one no green, right? Okay, so there will be first no green times second one no green until fifth no green, right? Okay, so what is the probability of no green? Yeah, 0.6, because 40%, we have a 40% is the chance to green. So that means 100% minus 60, I'm sorry, 40%, which is 60%. 60% no green, right? Okay, so there will be 0.6. Let me write down 0.6, yeah? So that will be same as 0.6 to the how many? 5, right? Yeah. Can you please calculate? 0.0778. Good job. Okay. Last one, C part. So we have which of the rare or unusual event. Okay. So we talk about the unusual. What this mean unusual? whether the probability is less than 0.05. The probability is less than 0.05, right? So which one is less than 0.05? The first one, right? All green will be, it's only 0.01, which is 1%, right? So C. All 5 green light will be unusual, unusual event since the probability is less than 0.05. Yeah. Okay, good. All right, so when you studied previous section, we had a disjoint, then we studied not disjoint, right? Here too, we had independent, means that one outcome does not affect the other outcome, vice versa, right? So we have a dependent in that case, means that one outcome depends on the other outcome. One outcome affects the other outcome, right? Okay, so let us do this one. So we have the example. So my daughter gets home first, randomly choose sports drink from the refrigerator. My son homes after that, right? And randomly select a sports drink from refrigerator. Okay, there are three orange and 2 fruit punch drinks, total 5. Okay, then first one, what is probability? My daughter randomly selected orange. So there's the number of orange divided by number of sample space, yeah? So how many sample space? It's a 5. How many orange? 3. Can you please calculate? Yes, 0.6. Second one, what's the probability of a fruit? Number of fruit punch divided by number of sample space. So 5 sample space. Fruit punch is 2. So 0.4, right? Okay. C part. What is the probability my son randomly select a fruit punch? Assume that choose orange. Yeah. Okay, this is hard to write. Fruit with orange picked. Orange picked, right? First. How about that, right? Okay. So what is the number of fruit? Still 2? Yeah. Okay, how many? Oh, oops. Okay, let me just rewrite everything. Um, okay. Oops. Equal to number of fruits. Because with the orange picked first does not matter, right? Yeah. So how about the number of fruits? Divide by number of sample space. In that case, we need without orange, right? So without orange, since the orange picked, one orange picked, right? Earlier. Yeah. Okay, so that would be how many fruits? Still two, but sample space is not 5, it's a 4, right? So 2 out of 4, which is 50%, 0.5. Yeah. Okay. Last one, still fruit, but in that case, my daughter picked fruit punch. Yeah, so let us do that. So the probability of fruit with the fruit punch picked first, right? Okay, in that case, number of I want to rewrite because I need this number, right? In that case, copy, paste. And then divide by sample space. In that case, also without fruit punch, right? Since the fruit punch picked earlier, right? Okay, so what do you get then? The sample space is a 4 instead of 5. And then how many fruit punch there? Because the fruit punch already picked by my daughter, right? So how many we have? 1 instead of 2, right? Which is 0.25. So 25% there. Yeah. All right. Okay, so let's take a look. Definition 2. So the probability that event F will happen, event E has already happened, right? So we call this is dependent. Two events are dependent. Then we are using, sorry, dependent event. Then look, we have what's the probability of F given event E, right? Then we are using this way, the probability of event F given E. Yeah, okay. So this is the same as what we did earlier. What's the probability of some pigs, fruit, punch? Given that, we read the vertical line, given that the daughter picks orange fruit, orange drinks. Yeah, that also we found 0.5. Yeah, given that, given, yeah. And we have what's the probability of some pigs, fruits, punch, given the the line, right? So given daughter picks fruit punch equals 0.25, okay? All right, now two events are independent, right? So two events are independent. Then we have the formula. What's the probability of event E? Then the probability of event E given that condition F. So this is given that, yeah. Given that. The line given that, right? So means that F has no impact on whether it occurs or does not occur, right? Because independent. Yeah. Okay, so let's take a look this question. Assume that two six-sided dice are rolled are the event. The sum is 8 and the first die is 3. Okay. So what do you think about this? We have a sum is 8, so this is 8. So 6 and 2, and then this one is 8. We can see that 5, 3, 4, 4, 3, 5, 2, 6. Yeah. The first die is a 3. Okay. The first die is a 3. We can see that. Yeah. Actually, we don't need this one, right? So because the sum is 8, right? So we need only this one, right? So this part. Hmm. Okay, so we can writing out. So we have what's the probability of the sum is 8? Given that the what is called the first die is 2. I'm sorry, the first die is 3, right? The first die is 3. Okay, then there will be number of, how do I write down? So I want to write down the number of sum is 8 and the first die is 3, right? Divided by number of sample space, yeah? Okay, in that case, only one, right? Only one. The number of sum is 8 and the first die is 3, right? So 1 out of how many sample space? So we have that those are sample space, right? So 1, 2, 3, 4, 5. That's it. All right, so let me write down the formula first. A little bit confusing, right? So we have independent, and then we call this as a conditional probability. conditional probability. So we have a probability of event E equal to probability of event E given the probability of event E, that is probability of event E and F divided by probability of event F. Okay. So in that case, look, sum is 8 and the first die is 3. I'm using that numerator, right? And then sample space. So what is the probability of, what kind of sample space we have to use? That will be number of sample space. In that case, probability of event F. The sample size of first dice is 2. Sample space of the first dice 2. Yeah, make sense? It's a 3. Sorry, why I keep saying the 2, right? Okay, so then the sample space is this one, right? So that will be sample space of first die is 3. So how many are there? 1, 2, 3, 4, 5, 6. 6. And then overlapping, sum is 8 and first die is 3 will be only one there overlapping, right? That part, which is this part, is the same as. Yeah. Okay, so it's only one. So 1 out of 6, which is 0.1667. Okay, so what I am trying to say. Oh, is this independent or dependent? Oh, no. Yeah. I should not use independent, yeah? Because it rely on, right? Yeah. But then we can interpret this way. We don't get the what is the probability of event E, which is the sum of probability of sum is 8, right? So we can use that definition, right? So this is now equal to probability of event E. So there is what's the probability of event E, which is the sum is 8, right? So there is the sum is 8. What's the probability of a sum is 8? So number of sum is 8. Divided by number of sample space. So sample space, oh. So we have 2 dice, right? So 36. We had the experience before, right? The sum is 8. So how many we have? 1, 2, 3, 4, 5 here. That is that part, right? So 5. So what do you get? This 1.1389. Yeah, it's a little bit messy. Yeah, I'm gonna put in here a textbook here. Yeah, answer, because it's a little bit messy. Make sense? So we need to conclude this is not independent, right? So which is dependent? So this one is orange is telling us this is dependent, right? dependent. Make sense? Okay, now let's take a look this formula. We have a multiplication rule. So we had a multiplication rule earlier for independent event, right? So let me review for that. So we had independent event. Then we have E and F. So what's the probability of event E and F? Then we multiply, right? Okay, what if we have a dependent, right? So dependent event. We have also multiplication rule, but then we have a conditional here. Let's take a look. So if we have probability of event E and F, then what's that formula gives us probability of event E times probability of event F, given that, given condition E, right? So given that. So E has already happened, given that. Okay. So let's do this one. The first one. We have 3 chocolate, 4 maple, 3 plain, 2 sprinkled donuts. Okay? So how many total? 12. Okay, total 12. Good. All right. So the first donut selected chocolate. So what's the probability of first chocolate and second maple? Maple. Okay. All right. So this is dependent, means that first chocolate and second maple. So when we choose the second maple, so we already happened the first chocolate, right? So then we can use that formula. All right, so there will be first chocolate times second maple, given that first chocolate, right? Yeah. So that is number of chocolate divided by number of sample space times number of maple and number of sample space. Yeah. So with first chocolate selected, right? Okay, so in that case, the sample space will be 12. And how many chocolate? It's 3, right? Okay, the second one, how many maple? 4 maple, but then sample space without chocolate, right? Without chocolate. Since chocolate is picked in the first, right? Like my son randomly select fruits and then daughter picked orange at first, like that. Yeah. So how many sample then? So we had a 12, and then first time we have all your chocolate picked, right? So we have 11 then, right? So 11. Okay, then can you please calculate? Yeah, so good. So we have a 0.0909. Yeah, very good. All right, so second one, the first three donuts are all chocolate. Okay, so second one, first chocolate, and second chocolate. I want chocolate. And third chocolate. Only three, right? Okay, so there will be no space. Let me write down. Maybe this way. Lot of writing. Okay, so that means first chocolate, right? So this one, it's okay. First chocolate, right? And times. So we need to follow the formula. So let me write down formula here. So copy, paste, no. Paste, no. Okay, so let me write down. Okay, so I wrote down here the formula, right? Okay, so first chocolate and times second chocolate, right? But then with the given that first chocolate, right? Times third one chocolate. Given that the first chocolate and second chocolate, right? Yeah, okay. So there will be the number of first chocolate divided by sample space times. Yeah, let me just writing out. How about T2 over number of sample space? But then in that case, without first chocolate, right? And times number of third chocolate with the first chocolate, right? So let me write down. Let me purge and then writing out, okay? Okay, so I wrote down everything here, in here, here, okay? So let's talk about that. How many sample space? 12, good, 12. And then the number of chocolate. We picked the first chocolate. How many are there? 3, okay, good. And times, how many sample space without first chocolate picked? 11, good. And then how many chocolate? Second chocolate with the first chocolate selected. So 2, okay, good. Then same concept, right? So how many sample space? 10, very good. And then third chocolate, how many number of chocolate left? Only 1, because first and second is already selected, right? Good. Now, can you please calculate? 0.0045. Very good. Okay, so this question is like the question asks us without replacement, like that. So when we see the question like without replacement, then we can just using sample size decreasing by 1, and also number is decreased by 1, like that. Okay, make sense? Okay, so I wrote down without replacement. Okay, and then you could not see earlier the number, right? Okay, let's do C. So C, we have you randomly select maple donut given that your sister and her boyfriend ate all the chocolate donuts. Means that there is no chocolate, okay? All the chocolate donuts means no chocolate left. Okay, so C part, maple. So we have a C part. I'm gonna use a different page with that. Let me put. Okay, C. So we want to know about the maple. What's the probability to have a maple donut? Given that no chocolate, right? Okay, so there will be number of maple divided by number of sample space, right? So in that case, without maple, no, chocolate. Chocolate. Yeah. Okay, so there will be how many maple? 4 maple, right? How many sample space without chocolate? So we had 12 minus chocolate is 3, which is 9. So it will be 9, right? So 9. Can you please calculate 4/9, which is 0.4444. Very good. Okay, so let us do last question D as the okay, tired and I want to eat the donuts. Okay, so use randomly select 3 donuts and none of them plain, okay? All right, so probability 3 non-plain, no plain. Okay, so there will be first no plain and second no plain given the first no plain, right? And third no plain given that first, no plane, and second, no plane, right? Okay. Let's think. How many plane? 3 plane, right? Okay, so we have no plane over number of sample space, and then second, no plane with first, no plane divided by number of sample space. In that case, the without plane, right? Without first, no plane. And, ooh, no space? Why no space? Oh, I have the, make it smaller. Yeah, make it smaller. Yeah, sorry, I cannot make it straight. All right, so times number of a third, no plane, with first and second, no plane, right? Divided by, and number of sample space, that's without first and second, no plane, right? Okay, so we had the sample space is 12 earlier, right? Then the next sample space will be 11 because without the first, no plane, right? And then third one, we have a 10 because take it out first and second, no plane, right? So we have that, right? So that will be 12, 11, like earlier, all chocolate, right? Yeah, 10. Then number of no plane. How many number of no plane? So 12 minus 3, plane is 3, right? So it's 9. Let me write down. No plane. 12 minus 3 equal to 9. Okay, then 9. Then next one is 8 because we have a second no plane with the first no plane, right? So 8, and next one is 7. Yeah, same concept as earlier. All three were chocolate, right? Okay, now can you please calculate? So it's a 0.3818. Yeah, very good. Okay. All right, so we have from the textbook important point. So since they bring up here, let me just talk here. Then we're gonna talk about later more. So what they say that the random sample from the population, we say the sample as independent. We treat the sample as independent if they are less than 5% of the population. Okay, so we're gonna talk this one later. Later chapters. Yeah, but since the book indicate that, I want to say it one time too. All right, so let's do this example. So we have a multiplication rule and complement to large population. All right, so we have a Pew Research Center say that 67.42% of eligible voters in the US. What's the probability that randomly selecting 6 voters voters who are all white. Okay, so probability of all white. Yeah, so there will be 6. Sorry, 6. Yeah, then independent. So we're using the first white and second white and third, fourth, and sixth white, right? Okay. So we have a 67.42, which is Beyonce method. 1, 2. To the left, to the left. So we have 0.6742 to the 6th power, right? We had the experience earlier, right? Can you please calculate 0.0939? Yeah. Okay, second part, non-white. Okay, so if we have white is 0.6742, non-white will be 1 minus 0.6742, or to get 0.3258, then there will be non-white over 6, right? 6 non-white. So first non-white and times the second and 6 non-white, right? Okay, that will be the probability is 0.3258. Once again, 6 power, right? 0.0012. Very good. Okay, the last one, they said that 6 voters with at least one non-white voter. Okay, so when we see that at least, we had the experience before, right? Means that 1 or more until 6 in the case, right? Okay, so when we see that at least, we can use complement rule most of the time. There is a couple times does not work, but it is working for every time. Yeah, complement rule. Complement rule. So at least one means one or more non-white, right? Voter. So more until this time is a 6, right? How much is 6? 6 people. Okay, so complement rule, how do we use? Oh, no space. Okay, so 6. Probability of at least one non-white, right? Voters. Okay, so there will be 1 minus probability of opposite statement, right? Statement phrase. Okay, so we have at least one means one or more, right? One or more until six. Until six, non-white. Yeah. What do you mean? This means 6 people non-white, right? Then opposite phrase will be opposite phrase will be all 6 white. Make sense? Okay, means 6 of non-white, right? Or 6 non-white. Okay, so there will be 1 minus the probability of opposite, so all white then, or 6 white voters. Yeah, okay, so there will be 1 minus all 6 white voters. We have a part, right? 0.0939. 0939 from A. So if we calculate, we get 0.9061. Make sense? Okay, so this will be last concept and then example. So the book indicate that phrase at least one is always complement of noun, because at least one means every time at least one or more, so they indicate everything, yeah, in the statements. So means everything in the question, right? So complement will be none, right? So they have at least one something. Then we make a complement 1 minus probability of none of something, right? So we think about every time opposite phrase. So 1 minus probability of opposite phrase. Okay? Because at least one something means everything. Yeah. So normally we are using none. Yeah. Let us do this one. Driving to school, so we did earlier. The first one, find the probability. So green light will be 40%, then not green will be 60%, right? 60%, which is 0.6, yeah? All right, so what's the probability of at least 1/5 traffic line is green? Okay, if we say that at least, we are using complement rule, right? So 1 minus what is opposite phrase? So 1 minus at least 1/5 means everything, right? In that case, it's all 5. Everything means all 5. Yeah. So means all 5 green, right? So then what's the opposite will be none of them green, right? So probability of None of them green. None of them, none of 5 green. Okay, so there will be 1 minus, what's the probability of green, right? 0.6, yeah? 0.6. Then none of 5 will be, we're using 5 here. Then what do you get? It's a 0.0778. This will be. Yeah. So 1, okay, hold on, 1 minus, because this one from the previous question, right? So there will be, then we get 0.9222. 0.9222. Make sense? Okay, let us do second part. We don't have a space. Okay, so probability that at least one of the 5 traffic light is not green. It's not green. Okay, let us do this one. Second part. So probability of at least 1 over 5 traffic lights is not green. Okay, so it will be 1 minus probability of opposite phrase. Yeah, okay. So at least 1 over 5 means all, right? Means all 5. 1 or more, right? 1 or more until 5, not green. So in other words, all 5 not green, right? Okay, then how do we make opposite? All green, yeah, good. All 5 are green, right? So that means 1 minus the probability of all greens, all 5 greens, right? Okay, so there will be 1 minus, what's the probability of a green? 0.4, right? So 0.4, and then all 5 is here. Then we had a probability earlier from the previous example. So we have 1 minus 0.1, that 1002, which is 0.9898. Yeah. Okay. So there is a 1% chance we will see the green light, and then 99%. So 99% chance that we don't see at least 1 red light. Make sense? Okay, so we are done for this section. So thank you for watching. I will see you in next video. Bye-bye.